There is a building in Sydney Harbor that 10 million people photograph every year, and almost none of them know it is dying. From the outside, the Sydney Opera House still looks the way it did the day Queen Elizabeth II opened it in 1973. The white shells, the blue water, the geometry that turned a former tram depot into the most recognizable silhouette in the Southern Hemisphere. But inside those shells, behind the soaring ceilings and the polished wood and the framed photographs of Pavarotti, something has been quietly going wrong for decades. Engineers have known about it, government reports have hinted at it, and the projected cost to fix it has now climbed to a number that, until recently, only existed in conversations behind closed doors. $8 billion. That is not a renovation. That is a rescue mission. And the strangest part is how few people are actually talking about it. To understand why the Opera House is failing, you have to go back to a decision made in 1959 that nobody wanted to make. The original architect, a young Dane named Jørn Utzon, had won the design competition with a sketch that engineers initially called impossible. Curved shells of that scale had never been built before. There was no formula for how to construct them, no precedent for how to hold them up, and no software to model what would happen to them over time. Construction began before the design was finished. Steel was ordered before the geometry was solved. Concrete was poured into forms that were being redesigned while it cured. The original budget was 7 million Australian dollars. The final cost reached 102 million. Utzon resigned in 1966 after a public dispute with the New South Wales government and never returned to see his building completed. What was left behind was a structure built under enormous political pressure, with materials chosen for speed rather than longevity and shortcuts buried inside walls that no one expected anyone to ever open again. Those shortcuts are now the problem. Concrete is not the immortal material people think it is. It looks like stone. It feels like stone. But chemically, it is closer to a sponge than a rock. Reinforced concrete, the kind used to build virtually every major structure of the 20th century, contains steel bars running through its core. The concrete is supposed to protect the steel. The steel is supposed to give the concrete tensile strength. Together, they are supposed to last 100 years or more. But that calculation assumed dry conditions, stable temperatures, limited exposure to chloride. The Sydney Opera House sits on a peninsula, surrounded on three sides by salt water, lashed by ocean wind, and baked by Australian sun for 9 months a year. Salt does not damage concrete the way most people imagine. It does not eat the concrete itself. It seeps through microscopic pores, finds the steel reinforcement underneath, and begins to oxidize it. Rust expands. Expanding rust pushes outward on the surrounding concrete. And concrete, for all its strength, has almost no tolerance for being pushed from the inside. It cracks, it flakes, it spalls. Engineers call this concrete cancer, and once it starts, it does not stop. It only spreads. By the late 1990s, structural engineers walking the inner ribs of the shells started noticing something they did not expect. Hairline cracks. Small at first, easy to dismiss. But they were appearing in places the original calculations had marked as zero stress zones. Internal reports, some of which were quietly released years later, described patches of concrete that had begun to lose density. Sections where a hammer tap returned a hollow sound instead of the sharp note of healthy material. In one survey conducted in the early 2000s, engineers identified more than 4,000 individual points of concern across the substructure. Most were minor, some were not. The building was less than 30 years old, and parts of it were already aging at twice the rate the original designers had assumed. The reason was simple. The concrete poured in the 1960s did not contain the corrosion inhibitors used in modern marine construction. The mix ratios varied because the project was rushed, and the steel inside it was protected by a thinner cover than today's building codes would ever permit. The white shells are not actually white. They are covered in 1,056,06 individual ceramic tiles manufactured in Sweden using a glaze recipe that took 3 years to perfect. Each tile is roughly 12 centimeters across. Each one was hand-fitted onto a precast panel before that panel was lifted into place. The tiles are not attached to the concrete with the kind of adhesive used in modern construction. They sit on a layer of bedding mortar applied more than half a century ago. That mortar, like everything else on the building, is aging. In the past 15 years, maintenance crews have quietly replaced thousands of individual tiles that had loosened, cracked, or fallen. Most of this work happens at night behind scaffolding, where tourists cannot see it. The replacement tiles are sourced from a small remaining stockpile of the original Swedish manufacturing run. When that stockpile runs out, and engineers say it will within the next decade, the building will face a question that has no clean answer. Do you remanufacture the tiles using modern methods that will not match exactly? Or do you let the missing ones stay missing and watch the most photographed roof in the world slowly turn into a patchwork? Hidden inside the ribs of every shell is something the original architect never wanted there. Steel cables, hundreds of them, post-tensioned, threaded through ducts cast directly into the concrete and pulled tight to give the shells the strength they need to stand up under their own weight. This was the engineering breakthrough that made Utsson's design buildable in the first place. Without those cables, the shells would have torn themselves apart within months. With them, the building has stood for 60 years. The problem is that nobody can inspect them. The cables are sealed inside the concrete. The ducts that hold them were grouted shut during construction to protect them from corrosion. But grouting, like every other process on the original site, was done quickly and unevenly. In some sections, voids were left inside the ducts. Voids let in moisture. Moisture lets in chloride. And chloride, given enough time, attacks high-tensile steel even more aggressively than it attacks ordinary reinforcement. Engineers have used radar surveys, electromagnetic scans, and acoustic testing to try to estimate the condition of the cables. The honest answer is they do not know. They cannot see the cables. They cannot replace the cables. And if a critical number of them ever fail, the consequences are not the kind that can be patched. They are the kind that close the building. Beneath the Opera House sits a sandstone shelf that has held up the building for 60 years. On paper, it should hold for centuries more. Sydney sandstone is one of the most reliable foundation materials on Earth, which is why so much of the city is built directly on top of it. But the foundation of the Opera House was not poured onto solid rock. It was poured onto a complex of piers footings and load distribution slabs that had to navigate uneven bedrock and the constant pressure of harbor water. Recent geotechnical surveys have raised quiet concerns about water infiltration in the lower service levels. Pumps run continuously to manage groundwater. Drainage channels have been retrofitted multiple times. The building is not sinking, but it is fighting a war against the harbor that no one expected to last this long, and the equipment fighting that war is itself approaching the end of its design life. The figure sounds impossible until you start adding up what is actually broken. Replacing the original reinforcement in the substructure Even partially requires removing concrete in zones the building was never designed to be opened. Cost estimates for that alone reach into the billions. Tile replacement at scale, including the manufacturing of new ceramics, runs into the high hundreds of millions. The cable system, if it ever needs intervention, has no easy fix because the access points do not exist. Add waterproofing of the substructure. Add modernization of the mechanical, electrical, and acoustic systems, most of which are decades past their replacement schedules. Add seismic retrofitting that the original design never accounted for. Add the cost of keeping the building operational while the work happens, because the Opera House cannot simply close for 10 years. Engineering consultancies that have looked at the full scope have arrived at numbers ranging from 5 billion to more than 9 billion Australian dollars over a multi-decade timeline. The 8 billion figure that has started circulating in industry reports is not a single bill. It is a cumulative projection of what survival actually costs. Spread over 30 years, it works out to roughly $270 million per year, every year, just to keep the building from quietly disintegrating. 3 options sit on the desk of every official who has ever been briefed on the full report. The first is to replace the most damaged sections of the building, outright rebuilding parts of the substructure with modern materials, and accepting that some of the original fabric will be lost. The second is to repair indefinitely, treating the Opera House as a permanent patient that will require continuous, expensive intervention for as long as it stands. The third is the most controversial. Some structural engineers very quietly have begun discussing whether parts of the building should be reconstructed entirely using the original geometry, but new materials creating a kind of replica fused with the original. Heritage advocates consider this option unthinkable. Engineers consider it inevitable. The argument between them is not really about the building. It is about what a building like this is supposed to be. A frozen monument, or a living object that gets to age change and be remade by the generations that inherit it. The Opera House will not collapse tomorrow. It will not collapse in 10 years. The structure is monitored, constantly surveyed regularly, and reinforced quietly whenever a problem becomes urgent. But every monument has a clock running underneath it, and the Opera House's clock is ticking faster than anyone planned for. The decisions made in the next decade will determine whether the building reaches its 100th birthday in 2073, looking the way it does today, or whether the silhouette that has come to symbolize an entire continent slowly transforms into something else. The strangest thing about the $8 billion question is not the size of the number. It is the silence around it. A crisis this large in a building this famous ought to be the lead story of every news cycle. Instead, it lives mostly in engineering journals and unpublished government reports. If you found this look inside the Opera House valuable, subscribe and stay with the channel. The next mega project we break down is even larger, and even fewer people are talking about it. One thing is certain: the Sydney Opera House was built to outlast the people who built it. Whether it outlasts the people watching this video is now a question of will, money, and time.